who don't know or haven't heard me yesterday, I'm Aviv Zohar. I'm a computer scientist at the Hebrew University. And today I'm going to keep telling you a little bit about interactions between blockchains and economics. This time we're going to ignore the consensus layer in mining and dive deep into the shenanigans that are taking place inside the blockchain. So we're going to assume the consensus layer is running. We have basically a service that runs and sequences transactions for us. And now I'm going to start to tell you what transpired. I think a bunch of this stuff happened after 2020, and maybe after COVID or during, and when decentralized finance started to kind of blow up. I'm still going to keep everything very, very simple. I'm not going to go too deep into anything, and I apologize in advance. There are like a million papers that I could be citing for everything. There will be mentions of some stuff along the way, but this is not even close to exhaustive. And this is our fairly ambitious agenda. I probably will not get to everything. That's expected, because it will take time. But I do promise you that because this is an Econ CS themed summer school, I will show code on the screen for the first time ever in this Econ CS. So now we can really say it will be CS. So the first thing I have to say is a topic I cannot ignore. It's like the very basic thing you would go to for an Econ blockchain interaction is the transaction fees that I haven't talked about so much last time. And I want to really just give you a quick overview of what happened there and what's happening with transaction fees in blockchains and how they're set. So first of all, the motivation for everything is we have a block size constraint when we're dealing with cryptocurrencies. We can't have infinite size blocks. We have to process them. We have to propagate them on the network. So the system is basically limited to some block size, right? So there's a resource that is limited. And the demand for transactions not only may exceed available space, it does exceed available space. People want to transact on cryptocurrencies, and this constraint is really, really bad. It does not allow cryptocurrencies to have high transaction rates. So, of course, what you need is a mechanism to allocate block space. And I've already hinted that there are fees that transactions are paying to the miner that chooses which transactions to include. So the first place to start is, of course, to describe what Bitcoin's mechanism is. Bitcoin's mechanism is just a pay or bid auction. Basically, every transaction, as it's created, states the amount of money that it will pay the miner to get accepted. And then a miner, being rational, chooses the highest paying transactions and puts them in the block. Right? That's the very natural thing to do.
Does the miner have a reserve price?
No, they're actually.
So they're required to do it no matter how low the winning bid is?
They're not required. It's it is coded. The mining software, the default one comes with this thing, but basically there were points in time where they would include zero fee transactions because blocks had enough room. And the idea is they are also getting paid by money that was created out of thin air. At that time, it was much more substantial, and actually transaction fees were negligible. Now, transaction fees in Bitcoin, at least, are becoming more prominent because the rate of money printing slows down. Still, there is so much demand that they're not using a reserve price. And right, you can think of it as kind of sort of a first price option of sorts, but you're selling multiple slots that are equivalent. And I'll show you, of course, that it doesn't work that way, and it's much more interesting. And of course, I think the main problem, if you think about this payment mechanism, is that users have to be strategic. They don't really bid truthfully. They want to shade their bids, right? If I have a transaction, I'm willing to pay $1 million to get it through. If everybody else is paying, a dollar per transaction, I will obviously not want to say $1 million. I'll say $2 or whatever. So I want to shape my bids. I want to basically bid lower than my valuation. And this means I have to start thinking about it. And we must remember also that all these transactions are visible to, at least the ones that were transmitted up until now, are visible to everyone else. So I can probably guess whether my transaction is going to get into the block or not. And maybe I'm even able to update my bid and raise it if I see that it's not likely to get into a block. So all of this makes the bidder's side, has to be more active to watch what's going on the blockchain. This is not a good design. Maybe you keep sending the same transaction again and again, which causes extra load on the system. That's not great. So now let's try some auction theory, and this is a straw man mechanism, just so I can talk about everything that starts to go wrong in blockchains. And this is the natural choice that economists would probably use, is like without knowing anything, you go for maybe the K price auction, right? So you have K slots in a block. Okay, in this case 4. So I'll include the highest paying transactions, and I'll take the 4th price, which is 20 here, and everybody here pays 20, right? So the revenue of the miner would be 20 times 4 would be 80, right? But this is where stuff in blockchains doesn't work as we'd expect. The miners are not the auctioneer that you have in standard economic theory that just follows the rules. They have their own self-interest in mind, and they can, unfortunately, manipulate the bids themselves. They can act as bidders as they want. So a miner, if we forced him to fill up the block, we forced him to take the kth price, he's actually going to create a transaction, just move money between his own accounts, and for example, in this case, pay 50. Right, this is money that changes. Right, this changes the kth price to 50. So this money goes from himself to himself. Right, he pays himself this 50, but he raised the price that these guys are paying. So now he's going to get 150, 150 from each one of these. So there's a clear manipulation done by the miner who just switched his price very easily. And this is something easy to do because he's deciding what goes into the block. Okay, so that's a problem. So basically, right, we understand that the miner is strategic. He can add fake bids. He can also ignore bids. He can drop messages in. It doesn't have to include anything in the block. So whatever the mechanism is, can only work on the information that eventually ends up on the blockchain. You cannot use things that are unseen. There's also a very important problem, and that's that side payments are possible. So a lot of people said, if we can't do this, the miner adds fake bids, maybe I will use the kth price auction, but I'll discourage the miner from raising prices and so on by taking the money and just giving it maybe to the next miner in the next block or something like that. The problem is that miners can actually collude with the bidders. They can say, you know what? You pay me, a side payment, not through the blockchain, and then bid have 0 fees on all your transactions, but I'll include them for you. So the revenue that we get from this block, I'm not getting it anyway. That passes on to the next miner, but that'll be 0. But I'm getting the side payment from you for 50, right? So that precludes any attempts to do stuff like shifting payments around, which we would maybe want to do.
When you say that they collude, you mean in principle they might collude, or you think?
Oh no, they are. We know they are. There's evidence that they're doing it. We know that there are. The way we see it is that certain exchanges, for example, certain accounts only have transactions that appear by certain miners. So we know that their transactions are not broadcast to the entire network. They're not available publicly for everyone to include in blocks. And so we assume we don't see the payments, the side payments, but we assume there are side payments as well.
But there's so many different miners, how can I as a user collude with, I don't know who is
If you're a big exchange, right? You're a Binance or someone like that. And you are talking to F2Pool, right, that we saw yesterday. And you guys, give us a
Big
discount.
players that
Yeah,
are-
big players are saying, I'll give you a stream of transactions. They're going to be secret, and we're going to see why the secrecy is also important for you from other reasons. And I'll pay you the transaction fees on the side. We'll do whatever together. We'll do whatever we want to adjust the bids so that together we make more money if the mechanism does something with that. Redistributes these payments and so on.
How are the side payments enforced?
So it could be just contractual between them, right? They can say it's not enforced on the blockchain. They can just say, we'll take all your transactions, we'll get them approved. We have a contract, we have some service level agreement, and we give you side payments, and they just agree.
It's
Right.
repeated options. It's repeated.
It's a
so they
repeated
can
interaction,
use,
so they-
maybe
yeah.
some,
It's a reputation.
Yeah, they have a lot of. A large exchange would be doing, let's say tens or dozens or hundreds of transactions per block. So every few minutes, they have more, and they can see that the miner are including them or not, and we know pretty much who mined which block. So they see that it happens, and it's very easy to have a deal like that. So you have to start thinking about it when you are designing these mechanisms. And there's another issue with this option. It actually has multiple rounds. It's a temporal thing. When a transaction doesn't get into a block, it doesn't go away. It's still there. It's still offering the same bid. So that makes this not a single auction for slots, but actually a repeated interaction, a repeated game of sorts. And users could have deadlines and time-related preferences, with the current mechanisms, there's no way to express them, right? Currently, transactions, you just give a number, so you don't say anything about whether you want it to get in fast or you're willing to wait a day. But users do have these preferences. For example, if I'm moving money between my accounts, maybe I'm not in a rush. But if I'm paying to buy some product and I'm standing, at the cash register, maybe I need it to get in faster. Okay, so all of these things make everything complicated and a little bit outside of current regular models for auctions, but not too far away that we can't do anything. Yeah.
One question: is the auction mechanism that you described is a guideline or is it enforced by the protocol?
Which you're talking about the pay or bid one?
Yes. Like, can you?
So pay or bid is actually enforced by the protocol. So the transaction, right, you're creating a transaction, I'm moving money from here to here, this is the fee, then you sign it. When a block is sent out afterwards, joining all transactions, there's an actual check that whatever the miner paid himself is the sum of the fees from these
They can, for
transactions.
example, ignore some they can ignore some requests with higher bids if they want.
They drop them out of the block. If they're not in the block, then nobody can enforce anything. But what they get is whatever is appeared in the block. Okay, so that makes this an interesting proposition. So then I had a paper with Ron Levy and Or Sataf, and we thought about what are we going to do. We didn't have a really great idea, but we said, okay, miners are actually, we can think of them as the monopolists. In what way? Every time a miner gets chosen to build a block, the others, the fact that there are other miners doesn't matter. He gets his turn now, so he can be greedy. He can choose whatever he wants out of there's a mempool full of transactions, basically a set of bids that have been submitted, and he can choose his price. So what's the likeliest thing to do? To choose, right, and these manipulations that we saw before, dropping this cave price out and putting 50 in, basically lets him set a monopolist price, in some sense. He chooses how many transactions, he chooses a price and basically includes everything above that price, and they will all just pay the price. So this is close to the case of the case item auction, in the sense that I can include stuff, but then I don't think about whatever the case bid is, but I think about the minimal bid, which is slightly different. So in this case, I'll just give him 150 from each transaction. So they all pay the same, and we give the miner the monopolist price. And then we said, okay, this is going to solve the problem of incentive compatibility for miners, at least for myopic miners, because the stuff he leaves behind, we're assuming this is gone, he'll never mine again, but in reality this miner could be a very large miner that is also very likely to maybe mine the next block and the next block after that and so on. So transactions that he leaves outside could be transactions that he himself will mine later, or that his competitors will mine.
Without collusion.
Without collusion, without any collusion, because of the temporal aspects. But if we think of myopic miners that are only looking at this round, this looked like something that would make sense to us. And of course the problem is you have to think about the incentive of bidders now. What about the bidders? And it's very easy to see in this example as well that bidders can shape their bids and change the monopolist price. For example, if I'm a bidder here, and I'm seeing all these other bids in real time, and I'm the one who bid 100, and I'm about to pay 50, I can do this. I can change my bid to 34. If you think about the set of bids here now, the optimal behavior by the monopolist, he can either include these two and pay 50, get 50 from each one of them, or he could include all three of these and get 34 out of each one. Right? So shading my bid here lowers the monopolist price, but I still get more money than.
Can I ask a very
Yeah.
naive question? I'm not sure what bidders see and they don't see. You were talking
Yeah.
now as though bidders can see all the bids.
Yeah.
But then a few minutes ago you were talking about the only things that people see are things on the block. So
Okay.
So-
Let me clarify this. So, if we do our job well and we ignore the side channels where they provide bids to each other secretly for a moment, and this will happen if our mechanism is good enough in some sense, then transactions are sent publicly to everyone. So the available transactions are seen. They're not in a state where everybody agrees about the set very strongly. So we cannot build a mechanism on top of that, right? Because maybe I missed one of them, I didn't get a message yet, and so on. The only thing that we really, really agree on is what's in the consensus protocol, and this is basically the stuff that's in the blocks. And so we cannot condition stuff on the protocol on things that are, we all know them, but not precisely, because we won't have agreement about them. The blocks themselves are things that we agree about. So when we construct a block, we can have a rule saying, we check these things, the price should be so and so, and that's what you pay. So we can create a monopolistic auction by saying, I'll let you include whatever transactions you want, and they all pay the price of the minimal transaction bid that you included. And we think of this as the monopolistic price because you chose where the cutoff would be between what's in and what's out. And you can see that the block is not necessarily full here, even. So we're not allocating all of the goods, which is, I guess, happens in monopolistic scenarios on purpose.
question.
Yeah.
Is there a threshold price, a fee, below which you have no chance of entering any block?
So that depends on the mechanism, right? But
In practice.
in practice, yes, definitely. If you could bid 0, for example, and you won't get in. I'll give you an example. At some point, we were publishing papers on Bitcoin, I think early in something like 2014, and somebody really liked one of our papers, and he sent me some Bitcoins on Reddit. And I gave them to my student, Jonathan Sopolinsky, and I told him, go buy coffee with it or something, I don't know what you're going to do with it. At some point, he wanted to share it with a co-author of ours. So he was a little cheap. He wanted to not to pay transaction fees. So he said, I'm not in a rush. Let's give 0 transaction fees. The transaction was then pending in this mempool of transactions for I think over a month. It just didn't go through, and he couldn't switch it to update the feeds for a technical reason. So basically, the money was stuck, which was very annoying. It's so very annoying part of how the fee mechanism works.
Is it a free storage on blockchain?
Sorry?
Can it be a free storage on blockchain?
It's off-chain, right? It's not on the blockchain. It was in the mempools of a lot of servers.
Yeah, but
It
it's
is some free storage, yes.
It's decentralized.
Yes.
It's pretty
Can I refine
reliable.
my question?
Yes.
Are you aware of a threshold that is not above zero, strictly above zero?
This changes. There is no absolute threshold. There are websites that I can actually show you later. There are websites that will follow the current state of the mempool, and you can see what's in there and how and what prices. I should have put a slide of that. If I would have remembered, I would have. There are amazing, really nice websites that have nice visualizations of the next block and what is the expected fee. So this is just a way to show that when you're bidding, you actually have a rough idea of what's out there in terms of amounts, and you can estimate, things like that. So I stopped in the middle of the story. What I showed you is that you can lower your bid here, but the insight that we had is, this is a very kind of tailored example. But if I told you, these fees actually come from a distribution, and when you see when you see 50s here several times, you don't know how many 50s are going to show up in a second or how many showed up. In a Bayesian setting, you're going to say, okay, maybe there's actually this guy who's shading to 34. You might say, maybe there's a bunch more 50s here because we just randomly had more. So maybe my shading of the bid will not work and I won't end up in the block. And then what we basically showed in our result is that there is almost incentive compatibility for the users. In the sense that their average gain, their expected gain from strategic bid shading diminishes, goes to zero as the number of bids increases. So if this was large and came from any reasonable distribution, then you wouldn't want to shade because that doesn't give you much. It'll give you a little bit. This example doesn't go away entirely. You save a lot of money here, but oftentimes it also makes you lose the transaction, and you just so being honest is not bad.
But there's another transaction 10 minutes later, right?
That's true. So one very big aspect that we did not solve is that the monopolistic price auction would do very crazy things in the temporal sense. If there might be a block with a single transaction, right? If you bid 1,000, for example, you also don't want to bid too high, right? If your bid comes from a distribution, but you are like at the very, very edge of it, like you have $1 million, you want to be truthful, maybe the miner will throw everybody out, just keep you, and charge you the entire amount. That's very scary for you. And the temporal aspect, we just, everything that accumulated would just go on to the next miner, which will then build a large block. So these things end up, cleaning up different ranges of prices, and we understood, I think, that this auction is probably not the right one to have, but it was one of the earlier papers, and we kind of wanted to put our stake in the ground to say transaction fee mechanisms should be looked at in the context of Bitcoin.
So this claim is about the monopolist pricing?
This claim is about the
And it's
monopolistic
just
auction.
because, the price is set by one of the guys and the likelihood the guy that is setting the price diminishes, or?
You're looking at the distribution and you're saying, okay, I'm going to shade my bid. What should I do? Whatever you do is the expectation is, you're right. Somebody will show up and push you out, or somebody will, right? That you only affect it if you go just below the current monopolistic price.
You need to be marginal, and the
Right.
probability of being marginal is like.
Right, exactly. So it's just right. You don't know. There's some, within some standard deviation, you might miss the right.
Yeah.
You might miss the exact place where you should be shading. And I think this could have been good enough in some sense, but it's not the best thing you could do. In parallel to us, Ethereum, while we were doing this, we are also aware that Ethereum started working on their own idea for a new fee mechanism, and their fee mechanism is a little crazy, in the sense that it burns money, a lot of money, everything pretty much in Equilibrium. So their idea is, you set a base price for the block, right, RH, and this base price is going to change but it depends only on the past blocks. So the current miner has no way to affect it. And then transactions pay, this base price. They can go over it if they want. Some tip, we call it the tip, which is optional. And then the mechanism basically burns this RH, destroys it completely, and the tip goes to the miners. They get a tip, So obviously the miners, they have to include only stuff that pays above RH, and they want the stuff with the higher tips. So this looks like the first price auction, but only with burning. It's a reserve price in a sense, right? You were asking reserve prices.
Right.
This is a reserve price, but you burn the reserve.
What is the logic behind burning?
So the logic behind burning is that if you give the reserve price to the miner, he can put in bids on his own, he can do funky stuff, so you don't give it to him. If you give it to someone else, then we have the side payment issues, so they decided to burn it. So if you think about it again, what does burning do? It's a way to reallocate the funds in some sense, from more of a monetary policy thing, right? Maybe neutrality of money, or you give it out to everybody else, everybody who holds money in some sense. You don't distribute it to the miners, you distribute it to every person who holds money. Their currency is slightly more valuable all of a sudden. Inflation, yeah. Or deflation, actually. Yes, negative inflation. So the thing is that you don't know what the reserve price should be, so they adjust it based on demand. The way you can, I'm saying demand in quotation marks, because you don't really know the demand for a block. So there's a formula, basically, that looks at a size of there's a target size for the block, which I denote as star here, and there's the size of the previous block. So miners are allowed to go above this target size or below it, based on how many transactions showed up that are willing to pay this reserve price, and then the price just goes up if there was too much demand. So if SH minus 1 is larger than S star, right, the previous block was more over the target, then the price would go up a little bit. Okay, so there's a 1/8 here and so on. And that depends on how large it was, and if the previous block was, for example, empty, then maybe did I miss something? If the previous block is empty, this is 0, and this is -1. Right? This is -1, so that'll make the block size, the price go down. So, in a sense, the formula itself doesn't really matter. You basically try to match whatever demand is for that base price.
So it goes down by 1/8.
1/8, but this could be continuous. This is not a discrete thing. The block sizes can be, whatever.
And then
Up
the block
to-
will reduce the next base price by 1/8.
That's what I mean.
Wouldn't it make more sense to have some moving average of sizes of previous blocks instead of one number?
This is what they chose. It might make more sense, but they react faster, right? It's a trade-off between reacting faster to change
Do
or.
you need to react faster? Is it really oscillating that much?
Surprisingly, I think it is. Yeah, it is. There are events when suddenly demand spikes. For example, we'll see about it later. When somebody sells something really valuable, everybody wants in, and within a single block, sometimes you have an explosion in demand.
Okay.
So this might even be slow. So I should say that Tim Roughgarden has a really nice paper analyzing this mechanism. He really set down the way to look at these protocols and made it crystal clear. And Tim shows in his paper that this protocol of Ethereum is typically user incentive compatible, except when there is a really low base fee. Okay, so if the mechanism somehow did not adjust yet, then at those points it's not incentive compatible. It's incentive compatible for myopic miners. Okay, again for those who are not looking at temporal issues, just solving for the current auction. And it is OCA proof. OCA is a notion of off-chain agreements, right? This thing that we talked about with side payments. It's a notion of collusion of sorts on the side. And the main issue is that the team says, at longer time scales, what the miners can do is they can push the base fee down to 0. They can actually discard transactions and make it look like the demand is low. So the price goes down if they collude together. And then the base fee will be 0, and you get in based on your tip. So you're back to maybe a monopolistic setting or a pay or bid setting, if they collude. And he says, otherwise, other than that, this crazy mechanism that burns money makes sense because it solves the problems that were with the side payments and so on. Yeah.
And what is an incentive compatible means?
So I think it's even dominant strategy incentive compatible, except for when there's I think too much open block space for the demand, right? So when the base fee is 0, or too much demand, too much contention for the block space, then it's not incentive compatible. Okay, I'm not going to go into it. I really recommend that you look at the paper. And then what also followed is a bunch of impossibilities showing, the team had all these caveats, EIP 1559 that almost does it, except for, and we had a caveat. And so it's natural that impossibilities were shown. I think this goes to Noam's talk yesterday. You show that things are impossible. So there was an impossibility resolved by Elaine Shi and Chang, basically with a different notion of collusion. There's Aviv Yaish and Yotam Gafni who are here showed, I think, the impossibility for the mechanism with the notion of that Rough Garden would have shown, and I think in parallel the team also showed the same or similar possibilities. And all these papers have nuanced way of relaxing the protocol and maybe achieving stuff. Okay, so there's more work on that. But maybe the bottom line of all these things is that there are no mechanisms that are, incentive compatible for even myopic miners without any temporal concerns for users, and that resist collusion of this of this weaker notion that has side payments, and in all cases, right, without any caveats.
They need to also obtain something useful because you can always have the mechanism that doesn't do anything. And it has
Yeah, so
property.
Ethereum has something, right? Here's a suggestion for a mechanism, and it is used. And one thing that I should say about Ethereum's mechanism, it solves for you exactly the problem of how to bid, right? You see this base price, this reserve price. You know exactly what will get you into a block. You bid this. You maybe add a little bit of a tip just to be sure. And then you know that the miner, even if there's more demand, the miner has a little bit of elasticity. He wants to put you in to the next block because that'll raise the price. He has an incentive to include you. So from the bidder's perspective, it's a very clean protocol, even though it burns money, and we don't like it for other reasons. But there's no reason to really hate it. I think just if you think again that this is a reallocation of the fees in some way to everyone who holds money via deflation. Right, so it's not a terrible mechanism, but I will say that it does burn. I think Aviv will probably know millions of dollars, billions. Okay, it burns a lot because fees on Ethereum are expensive. And so then there's work on temporal aspects. Aviv and Yotam have another paper, and Noam Nissan has something on the fact that you have serial monopolists here. And I think this is just the start, because the temporal aspects are really, really interesting for me. And we can also think about how to express in different ways the desires of users, which we didn't talk about here at all, whether they want the blocks in faster or they are willing to wait, and how we accommodate for that. So this is just to tempt you to look at this world of transaction fees on blockchains. Yeah.
Has the temporal stuff been analyzed with something like RL?
RL, I don't know. I'm not fully up to date on everything there. But, it might be interesting. Yeah. No regret mechanism. You can think of a lot of stuff that you could do. Right? So now I want to go to a different topic. Any more questions before I go on?
I read that the mempool is almost never full, or it was, last time it happened was years ago. Is there a mechanism that transaction get thrown out?
Yes. So the mempool is currently, I think, very large. It has a very large buffer. Depending on the cryptocurrency, I think Bitcoin has like 300 megabytes of transactions or something, very large. And they get evicted, and the ones that get evicted are usually the ones with the really low fees. So if this zero fee transaction, the reason it persisted for so long is that miners kept it in memory because they had nothing better to keep in memory. But once something enough 300 megabytes of transactions that pay even a little more are there, then you throw out the ones that are paying less, and you say, okay, maybe somebody will want them, they can retransmit them later if the price goes down, but I'm not going to remember them on my machine, because it's unlikely that I'll ever get to them. 300 megabytes at the time was 300 blocks worth of transactions, but so this is the backlog in some sense, but there's of course always more transactions coming in, so it's not like you just wait 300 blocks and you're done. It takes a longer time to compute that. Okay, so this is I hope I did these papers justice. Since we did the work initially, I've not been very involved in this line of research, but it's moving along, and I think getting interesting already. So I want to tell you a little bit about smart contracts, and I want to kind of build it up from the start. I don't have a ton of time, but I'll try to do my best with whatever time we have. So last time we talked about basically the blockchain encoding transactions. Alice sends so and so much money to Bob, and Bob sends it later to Charlie, and maybe Dave sends money to Eve. And we were sequencing these events in a blockchain. There was a sequence of actions. And we said, okay, that was the blockchain that allowed us to reason about the balance of accounts. And I think the nice insight is that you can sequence any data, and in particular, you can think of this as general computation. And now what we're sequencing is not transactions that tell us to move money, but actually calls to functions or executions of code. So somebody calls a function called adjust price and gives it some input, and this runs some computer, and then you do another transaction that calls a different function with different inputs and so on. And so this kind of mutates state of a computation, changes the values in memory, or does whatever the code told it. So now our model is that instead of having a bank here and sending it information to move stuff, we can think that we're trying to simulate a single computer, and there are users that are calling these functions on that machine with its code. But this time we're doing it on a blockchain, so the computer is actually simulated by each one of these nodes in the network. They're all running the same really weak computer. So it's not a supercomputing scheme where everybody's just doing different computations. They're actually all repeating the same computation and checking each other's work. Okay, so now we're simulating this. This is the new idea. And the manifestation of this idea is actually in Ethereum. Ethereum is this new blockchain that was built after Bitcoin, not so new by now. And what Ethereum does is it allows you to place code on the blockchain and then make these function calls to the code. And then every computer in the Ethereum network is in its head simulating the execution of this program. Okay, it's a little weird. So this is called the replicated state machine. And if you think about it, it's a generalization of this process, because this could be thought of as just a function call to move money from place to place, and it changes something in memory of the machine. Here we could do other arbitrary operations. Okay?
You haven't explained yet
Why do
you
this?
want to do this.
Why do this? Okay, so we're going to see a lot of examples of what you can build with this. So this is where smart contracts come in, this buzzword that you may have heard. So the nice thing about smart contracts, the thing we like to say, is that they're not smart and they're not a contract. Okay, so the name absolutely does not capture what they are. Smart contracts are basically a computer program that has three things. It has code, as a computer program would have. It has state, the current state of computation, what's in every variable. and it has a balance in the currency of the blockchain. So it's a computer program with a bank account. Okay? And this program can actually, when you run the code, it can change the state, you can assign things to memory, but it's also allowed to send and receive the money from its bank account based on the code. So there could be an instruction to send money. Okay, that's the new thing. Okay, so a transaction on Ethereum, basically what it does, it can send money to the smart contract and runs the code. Okay, so you can do both things simultaneously in one transaction, send the money and instruct it to do something with it. And the Ethereum is built so that calls are atomic in the sense that they are all or nothing. They either happen, they change the state, send money, they succeed, or if there's an error that is triggered during the execution, they abort, they roll back all the changes.
I don't know what it means to send money to the smart contract. I know what it means to send money to a user or to
So
a
let's think of a corporation, right? I establish a corporation. It's not a person anymore. It's an entity, right? And I can say, this corporation I can speak to by sending it maybe a form. Form 59-2 will, with a request or information, this would be equivalent of running code or something. And I put money in the envelope. The corporation has a bank account. And part of what the corporation does could be, paying other people. So here a smart contract is kind of this entity. Think of it as a legal entity.
Okay.
And now I can say, I can associate money with it. That's
But
what
does
it
some
means.
user or collection of users own that contract?
No,
Who
no,
owns it?
nobody. The corporation is owned, but it doesn't have to be owned in some sense, right? There are rules that govern how it works. That's the code, basically. The corporation will follow its bylines. It will, somebody will execute the rules, and it will issue money out and pay people, maybe employees or whatever, or investors or dividends or whatever, based on the rules that are written in there. But nobody necessarily owns it or does it. So somebody creates it and writes the rules, but then you step away.
The code is also on the chain?
The code is also on the chain. So there is a transaction at the beginning that puts up the code on the chain. That's a kind of a constructor. We can think of it in object-oriented code. You set this thing up, and then people can do function calls.
The actual code or the
The actual
hash
code.
of the code?
It's bytecode, but it's compiled code.
It's another kind of transaction.
It's but it also it falls into this paradigm because it could send money at the establishment of the corporation. It could give it money, and the running of code. There's a constructor code that actually runs and puts up bytecode on there. It's just input to a computation.
What happens if there's a bug? Do you need to?
If there's a bug, you're in trouble because you set this thing up. Unless you set within its rules the ability to change it, right? Then it doesn't change. And by the way, part of what you can encode into it when you set it up, you can set up a certain user with higher privileges. So you can think of someone owning this contract in the sense that the rules say that when this person tells me to do something, I will do it, and when other people tell me to do something, I won't do it. Right? So you could own it in some sense, but it's not necessarily the case. It could be treating everybody equally. And I'll show you an example. This is where code comes in. Okay? I will show an example. So this is atomic. The execution is deterministic. On the blockchain, you're not allowed to roll dice because the consensus protocol doesn't work if you have randomness in the data. Everybody has to run the same code, simulate the same computer, and reach the same results. So we have consistency between the different machines. So everything is deterministic. You're allowed to use pseudo-randomness, basically randomness based on a seed, but there's no real probabilistic action. Everything is public in the sense that we see the transactions going out to the blockchain, right? Just as we saw the payments before. So, and every node actually follows all of the execution, so everybody knows the state. There are no secrets that are hidden. Smart contracts cannot hide secrets from the world. And the code, as I said, may send money from its own account to other accounts, and that could be the accounts of other smart contracts or the accounts of other people. So this is what the abilities are. Okay, this is a little bit of a mind bend for people who see it for the first time. So here I promised an example. Yeah.
What if the code represents lottery, so still it cannot be probabilistic?
The source of randomness would be a seed, and everybody would be able to predict who wins the lottery in advance, unless you do something really special. There are ways of, this is what computer scientists do for a living. They try to think up of how to inject randomness into these things.
Some blockchains offer the source of randomness.
Yeah, so sometimes you have an external source, sometimes you have sources from the blockchain, but usually people don't do this well enough. It's actually somewhat of an open problem to have good injection of randomness into these things, or some randomness beacon. It's actually a very interesting thing.
Well, does the world have only one seed for all random numbers that are then supplied from a single source?
No, you can
Many
supply
sources.
seeds in the construction of a contract, or during one of the function calls. You can swap seeds, you can do whatever you want, right? It's general code, so anything is possible. So I want to give you an example of a code for a smart contract, and this is code for a Dutch auction. Okay, so this is a little, I think it's a good example for an economist crowd, because what's a Dutch auction? It's a descending price auction, and when you win when you say, I want the item, then you pay the price that is current, as it descends. So the first person to speak is actually probably the highest bidder, right? So there's a reason I chose the Dutch auction. It's actually a very compelling mechanism to use in blockchain settings. And this is because any other auction requires a lot of communication with the blockchain. If you're doing like a second price auction, that means everybody has to submit their bid. So you have a lot of interaction with the blockchain. This costs you a lot in fees. Whereas with the Dutch auction, you set up this auction. So that's going to be one interaction. The second interaction would be somebody wins, because the price is going to descend based on time. We're going to set it up so it decreases with time. And when you speak, you're done, the auction is gone. So 2 interactions, and that's fairly efficient. And as a result, I actually saw Dutch auctions being used in blockchain settings, which was really nice.
As the price is coming down, that has to be communicated, right?
So the price, we'll see how it's set up, but really, when you set up the auction, there's a start time, right? That's the setup. And then we say, okay, the price drops by $1 per block, or something like that.
I see.
So when you speak, if you speak on the 10th block,
Yeah.
you can calculate the price you can take out. Okay, so we set up a schedule for the decline. So what you're going to see is here's the state. This is actual code written in a language called Solidity. And we define here an item to be sold in some sense that has a function transfer from, that you can move, you can sell this item. So this is, I won't go into what that does, but this is basically the sellable item. We're selling something called an NFT, a non-fungible token. So this sellable item is represented here. You're saying what item I'm selling. This says who the seller is. It's an address in Ethereum, which is payable. You can send money to it, and you can't change it. It's the seller, okay? This is the person who's going to get the rewards, and there's the starting price, and the time we're starting at, and the expiration time for the auction, and the discount rate, how quickly the price drops as time progresses. So this is basically the state of the computation. It doesn't evolve so much over time because this interaction is going to be quick. We set it up, and then we're done. So, but in general, this we could do function calls that change these variables. And here's the setup. This is the constructor code. It sets up the smart contract. It receives from whoever's setting up, what's the thing we're selling, what's the discount rate, what's the starting price. And it says, okay, the seller is going to be whoever sent me this message, whoever set up this contract. The starting price is whatever he told me. The starting time is the block's timestamp. It expires at the block timestamp plus some duration that is fixed in advance. And there's a discount rate that is how fast prices decline. It basically sets the value of these variables. Discount rate is whatever we were told here. And then it says, I just check, require that the starting price is greater or equal to then the discount rate times duration. So actually, the price never gets to a negative number as we discount it. And here's we set up, we will remember what we're setting. And then this code is going to have just one interaction. Here's the function buy. You're supposed to call it. When you call it, you're basically saying, I'm willing to take this current price. So it checks that the current timestamp is before the expiration. It computes the price. There's a function here to compute the price based on, you can see the current time and the starting time and the discount rate. And then that sets the price. So this is the current price of the item. And then you say, okay, I check that the value that was sent with this transaction is greater than the price. Right? Is it greater than the price? And now if this is true, sell the item, nft.transfer from the seller to the person who called this function, give him the item, the refund of how much, maybe he sent me too much money, so I compute a refund, some money that I should send him back. And then I give him back the money. This is actually the smart contract paying a person back. So this is a command to send money, transfer money. And then the contract self-destructs. And the parameter here basically says, who do I transfer all of my remaining funds to? So the seller gets all the remaining funds after I destroy this thing. Okay, so this is the auction. We just implemented the Dutch auction. Not too much lines of code. Okay?
So I know how you transfer money. How do you transfer other items?
So we have to say what is another item. So I will tell you that the other item is also really represented in a smart contract like this. So the ownership is basically that in the other smart contract, it's recorded that you have something. Okay, you have you have some, you have a balance of some other token maybe or some whatever. So associated with your account is some number of how many of these items you have. And then I can call a function saying transfer this other thing. It'll decrement your counter and it'll increment someone else's counter. I could have included code for that as well. So transferring a token is also, usually when you implement another item over Ethereum, which is not its native currency, you basically write a smart contract. And that smart contract basically tracks how much of this new thing everybody has.
But how does anyone verify that you have this other item?
They can, first of all, you are allowed to transfer it by calling some function and incrementing the other person's. And there are functions like getPrice here that says, get me my balance. How much balance do I have? Or how much balance does a certain person have? Right? There's a function that will return a value. This is just tell you. It's a little weird. Yeah.
There is a notion that some people say that the essence of it is just spreadsheets, like immutable spreadsheets.
Spreadsheets may be a good model for people who know well spreadsheets. Well, yeah, that could be the right thing, right? But it doesn't really capture the idea of functions and right. So there is a way. So what I want to tell you is, in some sense, what does this contract do? Other than implement the Dutch auction, I mean, I could do a Dutch auction without this thing, right? I could just run the auction myself. So what's the difference? What's the deeper difference is, and the idea is that once I put this code online, I just define the rules of the game, and nobody can change them. So, if I was running a Dutch auction, I would tell you, maybe the winner would say, I want the money, the item. I tell him, transfer the money to me, and then I just don't. I refuse to send the item. I just run away with the cash, because I decided to. Okay, but this thing will never run away with your money because the code is set. It's set in stone. So now this has a condition that you have to satisfy, and if that happens, you get the item. And you get a refund. If your bid was somehow delayed, it wasn't included by a miner. You said, I'm sending money and I want to buy, but your message was delayed for a few blocks, and so the price even decreased a bit more. This has a refund for you, and it will always send it because the code said, do it.
But the item you're selling has to be electronic, otherwise
Yes,
no
it
one
has to
could-
be electronic.
Otherwise
It has to
couldn't
be
check.
on the blockchain here.
Yeah.
So this is a limitation of smart contracts. They can only look at information on the blockchain in other smart contracts, or whatever you supply them as input. They don't know any external information, and they don't control anything externally. That's a very big limitation of smart contracts. So I can make up new electronic items on the same blockchain. I can sell them, I can trade them, but they're all living inside the same bubble to a degree. Yeah.
Who pays for the code to be executed?
The person who's doing the function call pays transaction fees for it. Yeah.
The code needs to be executed on every single computer independently?
Yes. It's actually verified, and you can see that it's not really difficult computation. It's usually smart contracts are simple like this. They check a few conditions, they set a few variables, send a bit of money, and that's it. And that implements most of the economic mechanisms of interest. You don't need a lot of computation. You just, the more important part is the fact that it's done reliably, executed by many people at the same time who check each other's work, and so we guarantee that execution will be followed correctly. To some sense, in some sense. It's a commitment device for the rules of the game. Yeah.
I imagine this can be a source of scams if the person who wrote the code added some loophole.
Oh, obviously, yeah. I won't get into it today, but there are scams on the blockchain, and there is even more interestingly, there are honeypots for people who are looking to hack into smart contracts. So they send money, and they're actually wrong about the loophole, and their money gets stuck. And there are scams that attack scammers. It is so well evolved that there's a lot of stuff going on there. So the reason behind using smart contracts is that a human auctioneer might cheat or run away with your auction items, and this always happens in any third-party interaction. And smart contracts, their job is to eliminate third-party risk. You set the rules, they are set in stone. You know the rules will be followed, and the smart contract will do exactly what's in its code. Okay, and this is for better or worse. If there's a bug there, it'll do the bug, whatever you didn't mean to happen. This is a bad thing, but usually if you did your work well, then it's a good thing. Now I want to show you what you can build once you have this framework of smart contracts. So for example, I'm going to start with the decentralized exchange, which is a smart contract that allows you to swap one type of token for another. Okay? So first of all, I should go to something called the Oracle problem. And the Oracle problem is, as we saw, smart contracts can read blockchain data. They can look at they can call functions. They can read variables of things on the blockchain, but they have no access to external data. For example, if you wanted to know the current exchange rate between US dollars and Ether, the coin in Ethereum, you don't know, the code doesn't know it. You can give it as input, but it's not trusted information because somebody might lie about the exchange rate. It doesn't know the true exchange rate. So you might want to construct a piece of software that would tell you the price. And these are typically constructed in one of two ways. One way is to rely on this external injection of price data. So there would be a smart contract where you tell today's price is so and so. You come tomorrow, today's price is so and so. Whatever, the exchange rate changes, and then you just have to trust this source of information, and it's not necessarily correct. Another way is to use a market maker mechanism, and to basically offer on the blockchain to swap Ether for US dollars, or something closely approximating US dollars, a digital equivalent which is on the blockchain, and then you get price data based on what people are willing to do currently. Again, this is the way decentralized exchange has actually worked. They are both allowing you to do these trades, but also they effectively extract price information from the market. So let me explain
I don't
this.
understand what you mean by digital equivalent
Okay,
of US dollar.
so let's talk about the digital equivalent of the US dollar for a second. There's a company, for example, something called the Tether, and they say, okay, we're going to create an online token which we are going to peg to the US dollar. In what way are we going to do this? Every time you give me a US dollar in the real world, I'm going to give you this on the blockchain. I'm going to transfer this thing to you, right? I'm going to be willing to sell you a USDT, they call it, US dollar of tether, for $1. And every time you show up with a USDT and come to me, I'm going to give you your dollar back in the real world.
Well, how do we believe them?
So that's a good question, and it's a question that the Federal Reserve started asking, because USDT grew so much that if they're not fully collateralized, really backed by dollars, they're effectively printing money without backing. And the amounts of money that started rolling around in US dollar pegged coins, and several competitors actually arose, started scaring people. And there were rumors that some of them were not fully backed by dollars. So eventually there might be a run on the bank and people will really lose their money, right? If you know that they already gave up all their dollars in return, everybody's going to try and withdraw their actual dollars. But let's assume the existence of this coin that is pegged to the US dollar somehow. And there are coins that are pegged to Bitcoins and to other currencies.
But generally, I mean, they're regulated. So if it's an American
Yeah.
company that does that, and it says, I'm putting all my money in the bank, you could trust that as much as you would trust the normal US legal system.
They passed several audits.
They are starting to get regulated more heavily.
I thought the whole advantage of smart contracts was that you didn't need third-party
Right.
enforcement. Here you do.
No, you're right. So just to get this digital token that's equal to US dollar, you need outside.
So we see the problems here. Where do you need the regulation? Where the blockchain needs to relate somehow to the external world, right? To know that this thing is valued by $1. The blockchain cannot do that because there's no access to actual price information. Yeah.
So first, there was a story where Google then collapsed, right, with Terra.
Yes,
Yeah.
Terra and Luna, yeah, but they were, well, I won't get into that.
Okay,
So
yeah.
not exactly because they were backed, but they were digitally balanced without actual backing.
Okay.
Okay.
My second question is, why don't I see an equivalent of, say, S&P 500 in?
I'm not, I don't, well, I don't know that there isn't one.
Mm.
That there could be one.
Oh, so
Could be one.
Okay.
But then you're a broker, you have the company doing this has to have different regulations, I guess, on it, and which makes it more difficult. But let's talk about automated market makers for a second. Maybe you guys know this. This is relatively old stuff, I think. So what I want to show you is something called the constant product market maker. And it's out of a general theme of a general class of market makers that are constant function market makers, but the function here is going to be product. Market maker actually holds some amount R1 of token 1 and some amount of token 2. And it will accept trades between these two tokens. So you can say I'm going to give you some amount of R1 and take away some amount of R2. And it will accept changes of balances that shift it to R1 prime and R2 prime such that the product of these two remains the same. Okay, this is why it's called constant product. And this implies, right, that the invariant that it's keeping is some R1 is C over R2. That's kind of a way of thinking about the relation, which is equivalent to this for whatever C is. And this implies an exchange rate between the two tokens, right? If you differentiate, right? If you want to do an increase in R2, how much R1 should you give? If you want you want R2 tokens, so what should you give in R1s? So you just derive dR1 by dR2 is, right? You differentiate this. This is minus C over R2 squared. C over R2 is just R1. So this is minus R1 over R2. Okay, so basically the price is the relation between the two amounts. Okay, so this is like if you added this tiny differentially, a tiny differential of one, you get a certain amount of the other, and this is the exchange rate. Okay, so market makers of this form are very nice. First of all, because you don't need any person to run them, right? They can be run automatically with software, right? If you give me so and so amount, I can compute how much you get from the other token. So we can implement them in code in a smart contract. All they need is holdings of tokens, and we already know that smart contracts can hold money. And they also guarantee that any losses from trade will be bounded for any series, infinite series of trades, because you start with some R1 and R2, but at most, after an infinite number of trades that you accepted, you might lose, one of them or the other, but no more than that. So whatever you started with bounds your loss for an infinite series of exchanges.
This exchange rate is things that about Ethereum and dollars. They exist in the world with demand and supply determining the price.
Yes. So what happens if the price? Let's say the prices are the same, right? But then in the real world outside, Ether goes up versus the dollar. So you will rush to the blockchain where you can buy Ether cheaper, and you will pay. You'll exchange. Ether for dollars, and you'll up until it reaches the same price, right? So in some sense, this drives you to set the record straight with this market maker, and now the price data is correct. But
So
otherwise, you have an arbitrage opportunity.
You create arbitrage opportunities and
Yes.
this results in.
But the funny thing is that even this thing is behind, always in terms of information. It's lagging behind, and it's always trading with bad prices. Its losses are still bounded. This is the magic, right? That's the magic. It's always informationally inferior, but still, arbitrage works somehow against it, always, all the time. But it doesn't lose over an infinite sequence of events, right? So it runs forever. So and it keeps running, which is great. So an ideal mechanism to automate. Yeah.
Is this the thing you can actually invest in, like on Binance or something?
This is one of the things you can invest in. Yeah. So what really they do is they don't really exchange it exactly for this rate. They take a fee. They give you the fee to whoever set up the mechanism, and some of it to whoever provided the liquidity. Okay, so you can actually get money on you. So there's another side to this. Whoever provided the liquidity collects some of the fees. Right. So this is a way to invest in cryptocurrencies. But the mechanism itself, in its cleanest form, just gives you a price oracle, but also provides this ability to exchange token for token, and it's always there. Every time you want to exchange something, up to the amount of the liquidity that it has, right? There's a limit, but it will be always willing to trade for something, for some price. So now, this creates arbitrage opportunities in abundance, because when you have something trading ETH to USDC, there's always this is another derivative of the US dollar, not Tether, but from another company. Then there would be a competitor smart contract that has another pool, and it will also have a price. And if Alice goes and trades with these things, the balance here would change. Maybe she takes ETH and gives USDC. Then somebody who's looking at both of these will say, wait a minute, there's an arbitrage opportunity because Alice did not trade on both of them. And so I can move ETH from here and give USDC here, and I'll come out on top. Actually, without any investment, I'm going to make money from arbitrage here. And so a lot of people started looking at the blockchain and doing arbitrage. And the problem is compounded because there are a lot of tokens on Ethereum, not just two. And when you look for arbitrage opportunities, they can be complex. Maybe you move purple coins from here to here, you get yellow coins that you move here, which gives you blue coins, which gives you light blue coins, and you've closed the circle, and somehow you end up with more money than you started. So an arbitrage opportunity, which is wonderful. And it's almost impossible for an Alice that buys some currency to really think in advance about all the trades that she's opening for arbitrage. It becomes increasingly complex. Okay, so now imagine the people who are trading on the blockchain also create arbitrage opportunities, and there are all these people hungry for free money that's left on the table, and they start transacting as well. They start competing to get these arbitrage opportunities. So we have more action on the blockchain. And now I want to show you quickly another platform that you can implement with code. And I want to convince you that it's another interesting thing. So this is actually a collateralized loan platform. So here's what you can do. It'll let you borrow some amount of tokens. Okay, so yeah, think about it for a moment. If you come to a smart contract, a piece of code, you say, I want to borrow 1,000 Ethereum. What's the problem? If it gives you 1,000 Ethereum, you might never repay it. You're gone, you don't show up. So you can't have just a regular lending thing, because usually in the real world, if you borrow money, there's an external enforcement mechanism. If you don't pay it back, you go to jail eventually. But in the blockchain, we can't send you to jail. So we can't just give you money without collateral. You have to actually deposit money into this thing to get a loan from another thing. So this comes out with a little strange. You actually have to provide collateral that's worth more than the thing you're borrowing. So this is not really a loan, right? You think of it as a loan, but you put in more money to get less. That's the weird thing. And right, the example is I'm borrowing $800, but I deposit Ethereum in the amount that's priced at $1,000 of ETH as collateral. So already we see something that collateralized loan platforms need. They need to know the price of your collateral denominated in the thing you're borrowing. They need to know how to convert prices to know that something that they put up as collateral is worth more than the thing they're lending. They need price oracles, basically.
Normally, when you have a collateralized loan, the collateral is worth what you're borrowing. Why should this be more than?
Oh, we'll see. We'll see in a second. You have to hedge against changes in the exchange rate.
What keeps you from providing the same collateral to to support multiple loans?
Oh, when you provide collateral, you actually transfer it to the destination, and because it's a smart contract, you know that it won't steal your money. It will use your collateral only as the code says, and it will return to you the collateral reliably when you repay the loan. So that's a benefit of using smart contracts. So you feel much more safe giving it your money if you understand the code. Okay, that's I don't know if you should feel safe, but people do. And then the borrower still pays interest rate. Okay, so we think of it as a loan. What's the difference here? We can think about it differently. Wait, let's contrast it with the previous mechanism. In the previous mechanism, we gave Ether and we got US dollars and we're done. Here, I give Ether and I get US dollars as well. Right? This is not this. But now I have to pay interest. So what's the benefit? Regardless of how the future price of Ether and dollars changes, when I repay the loan, I will get exactly my collateral. Okay, so I'm basically detaching the price. If I was exchanging via a market maker, and I took money, and I later wanted the Ether back, maybe prices have changed. Now this kind of says you're going to get back your collateral if you just give me these funds.
So it's just a bet on exchange rate.
Yes. So this is okay. So now I want to say before that, I want to say what happens if the collateral's value drops below the value of the loan. The borrower is never going to show up and reclaim that collateral. He just, it's not worth it. So the smart contract that runs this tries not to lose money. So it basically will offer the collateral for liquidation. It'll sell the collateral to try to cover the loan itself, if this ever comes close to some margin from the value. Okay, and it actually sells it at a discount to make sure it really tries to sell it fast. So this is a kind of a regular idea in these sort of things. Not just in blockchains, right? So now why use a collateralized loan? Let's see exactly what it does. So what I want to show you is that it allows you to enter a short position. right? If you borrow money from someone, this is a way to create a short. So let's say Alice has 4 Ether coins, and she thinks the value will rise of these Ethers, but Alice really wants to bet against the US dollar. She thinks the dollar is going to go down. So what can she do? She goes to a platform, a lending platform. She deposits her Ether and takes out a loan. So I'm assuming 1 Ether here is worth $1. She just gets $3 less than she deposited, right? So there's more collateral here than bills that she got. And then she doesn't hold the dollars because she thinks the dollar's value is going to go down. She goes to an exchange and gives them, $3, but she only gets 3 coins, right? Because it's less than the collateral she had to put. But then the value, right? The value eventually changes. Let's say she was right, and the value of the dollar is lower. So she wants her 3 bills back. But now they cost less. Instead of the 3 coins that she got, she only has to pay 2 coins to get the $3 bills back. So she gets the $3 bills back. You see that she has an Ether coin remaining here. And now she can redeem the collateral. The collateral is not based on price. It's just if you give back the $3, you get all 4 coins back. So she gets the 4 coins back, and she made money shorting the US dollar. Okay, what's the risk for her? If she's wrong, right, then Aave is actually going to, right, before she does this redemption, she might be in this situation. If she's wrong, Aave is going to actually liquidate her position, and she's left with less money than she started, which was 4 coins, right? So she can bet against something. So now we have short positions over things with this collateralized lending platform. This is the reason why people use it. So I'm actually short on time. I'm going to skip this. I want to get to a slightly more interesting thing. I have a little bit of critique on how these things work, which is interesting, but we don't have time for it. I want to tell you about flash loans. Okay, sometimes to be able to execute a trade, you need liquidity. There are cases when you can't execute a trade, even though you know you should be able to. I'll give you an example. Let's say you see an arbitrage opportunity to take money from here and get it here, and take money from here and get it here. This thing is going to leave you with a net profit. But you need money to get it started. To realize this opportunity, you need to, right, you can't just take ETH here, you have to give US dollars. You have to trade with the mechanism, so you need something to give it, to get something back. Then you move it here, you get your money back, and then you will come out with a profit. But you need initial liquidity to get this started. So this is one example. Another example is if I had a collateralized loan in one platform, and I wanted to move it to another platform that maybe offers better interest rates on the loan. So what I had to do is I had to repay the loan, get this thing, but I need money to repay the loan with. And then I move it and I take out another loan. So I need liquidity to move this from place to place. And maybe I just, I end up with a similar position, so this is only temporary liquidity. And another situation is when somebody liquidates one of these positions, and I want to buy the collateral at a discounted rate, and then I'm going to sell it instantly and make money. Then I need liquidity. So there is a way to actually take a loan from a smart contract and repay it instantly. It's called a flash loan. So basically, think of something like this. This is a function that I call on another contract. And this gives me some amount, it gives me money. Then it calls a function on my smart contract, do something with this money, and I choose to sell, buy, trades, do the arbitrage, whatever. And then at the end of this, I repay the loan. So I need to remind you of 2 things. One is that transactions on Ethereum are atomic. So this thing always, if it took money and returned it, everything runs correctly. If I did something here and I'm unable to return the money at the end, then this whole transaction rolls back. It's as if I never took the loan. Everything is canceled. So this will trigger an error if you cannot subtract the amount from my account, and it'll cancel everything I tried to do. So the loan is actually an instantaneous thing. I get the money, I do a lot of trades with it, I give it back in the same atomic action.
But it feels like a cheat because Go Wild can take a week.
Go Wild is running on the blockchain instantly within a transaction. It doesn't take time.
Like a program that runs in a single block, right?
It's included in a block. It runs after the previous transaction and before the next one, right? So it's
Go Wild
sequenced.
specify everything and it needs to run instantaneously.
Exactly.
Well, does that stall the block if Go Wild turns out not to happen?
No, it doesn't stall the block. What it makes is the transaction just fails. You pay a lot of transaction fees for it, but it didn't do anything. Okay, so this is an instantaneous loan. What is the risk to the lender? Nothing. You're not going to run away with their money because they get it back at the last line here. Otherwise, this whole thing aborts. They don't get their money back. So zero risk to the lending party, but a lot of power to the borrower. Now you can borrow $1 billion, do whatever you want with them, return them at the end. Okay, wreak havoc. If maybe would be better than Go Wild. Okay? So you can be, it's very, and what should be the interest rate that you pay? It's instantaneous. You didn't hold the money for any period of time. You know, the liquidity could have been used after you by the next transaction without any disruption. So zero interest payment, you pay some fee, but it's not based on anything. It's just a service fee or something. It's not an interest rate problem. Right? You didn't occupy this liquidity for any time. It was there held for a brief instant. And so we see things like that. You read the papers, you see a decentralized finance project, BZX, has suffered an attack in which a hacker successfully gamed multiple DeFi protocols to extract $350,000 from the platform. Right? Also, what it gives basically is leverage, right? Liquidity for people who are finding opportunities. You can think of them as arbitrage opportunities, but really they manipulate price oracles in a specific way to make sure that there is an arbitrage transaction that is mispriced to give them a lot of money. So the BZX attack, I won't go over the details, but basically this thing executed a series of trades, and the interesting part is that it used one of these pricing oracles that had really low liquidity, so that if you executed a very large trade on it, you could inflate the prices on that price oracle by a lot. They jumped by a factor of 2.5. And then some collateralized loan protocol was looking at this price data to decide on what amount of collateral you need to put. The collateral was overvalued, so they ended up putting very little collateral, getting out a huge loan, and then eventually, you know, the prices adjust back, but you already took a huge loan based on that, and they made a lot of money.
And everything like this attack was atomic?
This attack was atomic. All of this thing happened within the one function of the Go Wild. So they never saw it coming. They lost $350,000 like that. And of course, the nice thing here is that the second thing is that they were attacked again for $645,000, right? So and again, like that, somebody did another one on a different mechanism, slightly different one. So you see a wild stuff going on in the blockchain. Let me try. I'm not going to answer questions for now. I want to try to do one more thing. I want to show you how the shenanigans on Ethereum grow by a lot more. I'm going to skip this. This is our image of why this is happening. So miners can manipulate the order of transactions. If you remember, I'm going to show you how they use this to attack these systems. So let's imagine Alice is interacting with the smart contract, and she wants to buy 100 Ether with the USDT. She wants to exchange, right? So she creates a transaction, sends it to the network, and then a miner is now looking at this transaction. He says, okay, I'm going to try and include it in the next block, and then Alice will exchange. The problem is that Bob is also there. He's also looking at this transaction. He says, whoa, 100 Ether is a lot of money. this is going to raise the price of Ether. So I can take advantage of this. It still isn't in a block. It didn't happen yet, but I know it's going to raise the price of Ether. So what Bob is going to do is he's going to try and buy 20 Ether before Alice. Then Alice will buy 100 and the price will rise. Then Bob will sell his 20 Ether for a profit instantly. And this is called a sandwich attack. Okay, this you can think of this as the equivalent of you know, high frequency trading on in the real market, in real markets, but in the blockchain scenario, where if you know something will change in price, you want to buy it first and make a profit.
How does Bob make sure he gets in before Alice?
Oh, that's the problem, right? So he can try all sorts of tricks at the beginning. He tries to give this transaction a little bit higher fees, so it's included earlier in the blocks, because he's relying on a heuristic that miners are including higher paying transactions, you know, greedily in order, and they will put this transaction first, and then he tries to have slightly lower fees to have this transaction come in second, but he really can't guarantee it. If he succeeds, he makes money. And here's the problem, right? Dave is also looking at this. Dave says, wait, Bob is going to buy 20, and Alice is going to buy 100. I want to make money too. So I'm going to try and buy before Bob and Alice, and I'm going to try and sell before they do anything. And of course, here stuff gets messy, and the miner might so the problem for Bob here is that this actually might erase his profits because he's buying at a higher price than he expected. So usually he doesn't just buy. He can condition the purchase because he's allowed to run this through a smart contract. So he has code running. He says, I'm calling a smart contract that checks the price. If the price is P as I expect it to be, then buy, otherwise don't buy. And then what happens is, because something happened before he got there, he doesn't do anything, but he still pays fees for it. And the sell doesn't happen because it doesn't have Ether to sell. So this crashes. So these two transactions were on the blockchain, but they took up space, but they aborted their action. And the worst thing is that they could, by trying to manipulate the timings here, they might be wrong about what the miner does. The miner actually could sequence things in a different way. And then, this thing gets canceled because this was bought, but then this guy buys and sells the same item and reaches the same price and just pays fees. And this was the state of Ethereum. At some point in time, everybody was just trying to front-run, sandwich attack each other, and they were tripping over each other.
Why doesn't the miner try a sandwich operation?
And the miner could try a sandwich operation and just drop all of these and make all the money himself. And the miner could take payments from these guys to sequence blocks as he wants and actually extract some of the profit for himself. And this is exactly what happened in Ethereum. These searchers that exploit arbitrage, front-running opportunities showed up, and they started tripping over each other and losing money in transactions, but there was also value to be captured there. So a large fraction of transactions would fail, and then new players entered the market.
I would have thought since the miner can control the sequence.
Yeah, but the miner has to be
able to
the miner is
exploit
really
all
good
of
at
the
mining,
arbitrage.
and someone else is really specialized at finding arbitrage opportunities.
So the miner doesn't know enough about arbitrage.
You need a whole operation to find these sophisticated arbitrage. So now what happens is there are guys that are called block builders that will assemble a block for you, and they offer it to the miner. Here's the block that you should mine, and if you mine it, we will pay you money, basically sharing the revenue that we got from this specific sequence of transactions. Now you're going to get a part of it. And builders actually auction their block between different miners. And there are relays that are players that receive transactions and keep them secret, and will give them only to specific miners at specific times. Or you can send a block through a relay, so the miner is guaranteed, here's a block that will give you a certain amount of money, but I keep it secret from you, because if I show you this thing before you mine it, you can actually repeat the sequence of, you can replicate this thing on your own and mine it. So the relays are actually devices to keep this information secret, so the miners can buy blocks from the builders without knowing their contents, but they are, by reputation, they are guaranteed that these blocks will be correct and they will extract the correct revenue and give them money. So this whole ecosystem of users and searchers and builders and relays eventually give the miners a block to build. Okay, so a lot of shenanigans on the blockchain. And this actually starts to make the system more and more complex. And I don't have time, but I have what I wanted to show you is a way to attack them, actually, using these. The fact that, you know, this guy builds a block, he doesn't know if it gets mined. To build a block, he has to run the program. So what we do is we give him a really difficult program to run, and then we make sure that the block is never built by making sure that it's not allowed to create a block in this form. So we have all sorts of tricks. And that, from the computer science perspective, says, you know, this separation, which makes perfect sense from an economic perspective, where we're extracting value, right, at the expense of poor saps that, you know, left arbitrage opportunities or, you know, broadcast their transactions in the public in some sense. This system evolved, but it also makes the protocol more less resilient to attacks and more susceptible. All right, so I'll stop here because we ran out of time. Thank you all.
Thank you.
And if you have questions, I'm going to be around.
Very much.